And this is progressing, and now we add back this. Okay.
Okay. So can we enlarge? If we
I hope so.
Yeah, it's good. It's all.
Okay, so please. Uh, uh, Gravity. Yeah. Okay. Now, should be working now. Yes, sorry for the
No,
confusion.
no, it's okay. So, as we said, that we have our system of differential equation, and we are going to analyze this system step by step. My first step is taking f of r, which is the first derivative of f of r to be constant, and taking k1 to be equal to 1, and taking the electromagnetic is equal to 0. So if we return it to our field equation, this will return us to, from here, if I take k1 equal to 1, and if I take f equal to constant, and if xi equal to 0, in that case, the system will be solved analytically, and our system solution is given by this. So this is the well-known BTZ solution of generativity. So our system is consistent when we return to Einstein field equation. Okay? So let us analyze the second case. The second case will be taking f of r also equal constant, and the k1 equal 1, and the xi not equal to 0. In that case, this will be the system whose solution will be given by this one, which is also the charged BTZ of Einstein. So till now we didn't get any new solution. So the third one, the third case, and of course, before I go to the third case, if we put here the constant C3 equal to 0, in that case, we recover the BTZ that we derived in the first case, this one. So let us discuss the third case where f of r not equal to constant, and both k1 equal to 1 and xi equal to 0. So in that case, we will get k, which is the only unknown, to be by this form, and the form of f of r. This is the derivative, the first derivative of f of r by this form. Okay? As we see that if we put C4 here equal to 0, we recover this case, the first case, which is of BTZ. So if we put C4 equal to 0, in that case, we recover the BTZ of Einstein. So the main deviation that different from Einstein, or the BTZ of Einstein, come from this term, which gives this form. Just we derive the solution, and after that we will discuss its relevant physics. So this is the third case where we take f of r not equal to constant, and k1 equal to 1, and xi equal to 0. So the first case is taking f of r not equal to constant, and k1 equal to 1, and the xi not equal to 0. And in that case, here is the form of k, and here is the form of electromagnetic field, and here is the form of F of R. So in that case, if we put C4 equal to 0, we recover the charged case of Einstein. And if we put C3 equal to 0, we recover the previous case where F is not equal to 0. Okay, here is dialogue, is the diagonalistic function, which is defined by this form. Okay, where dialogue of 0 equal R squared over 6, and the dialogue of 1 equal to 0. So our last case is the general case where we take F not equal constant, K1 not equal to 1, Xi not equal to 0. This is the general case. Okay, where F not equal to constant and K1 not equal to 1. In that case, sorry. Before this case, we are going to discuss when this is the previous case where we discuss this is not equal to constant and this is not equal to 1. This is the general case. F not equal to constant, K1 not equal to 1, Xi not equal to 0. In that case, we solve the system and obtain this is the form of K, and this is the form of K1, and this is the form of F of R, which is the first derivative given by this exponential, and this is the form of the electromagnetic field. As we see that this is a new solution and generalized new charged BTZ solution and generalized the Einstein BTZ. So in that case, if we take C7 equal to 0, this means that Xi equal to constant. So we recover the previous case. And if we take C6, the constant C6 equal to 0, in that case, K1 will equal to 1, F of R will equal to 1, and we take C6 equal to 0. In that case, we recover the charged BTZ. So we can recover the previous case by playing on the constant that we drive. So we have up till now 5 solutions. 2 of them are well-known solutions, the BTZ and its charged form. So we are not interested in studying these 2 cases. So now we are going to discuss the physics of each case. The first case of our study is to write the metric and show the asymptotic behavior of this solution. So for the case where F not equal to 0 and K1 equal to 1 and Xi equal to 0. So in that case, this is the metric. So we make it asymptotic for small r and for large r. And this is the asymptotic of this light element. As we see, this is this one. This the asymptotic form of the metric as for large r, and this is asymptotic for small. So as we see here that of course there are contribution. See the first 2 terms there, no, for small r, the first this term and this term are the well-known of BTZ. So there appears this extra term which comes from the modification, which comes from value of f of r. So, for example, this one and this one. And you can see that if this term, if C4 equal to 0, in that case, we recover the BTC small r. What happens if we take C4 equal to 0 for larger? This is not allowed. As you see that C4 in the denominator. So it's not allowed for large R to put the constant C4, which is the main deviations or the main modified term that gives this new solution to be equal to 0. Okay, so of course the referee asked me what does this means. I was having no specific answer because we need to extend the study of this solution. We need to calculate the geodesic and see what will happen for this solution for large R, what happened when C4 equal to 0. So generally, the solution behave like de Sitter or anti-de Sitter, depends on the size of lambda effective. But for small r, the solution will behave. For large r, the solution we don't have its good behavior because it tells us that we are not allowed to put the constants that make the deviations to equal to 0. So in that case, we can't recover BTZ for large R only. So after that, we calculate the invariant of such a solution. So this is the invariant. So let us speak about the invariant, for example, for Ricci scalar, for Ricci tensor squared, for Kretschmann, for small r. So for BTZ, Ricci scalar generally equal to 0. But here, for our solution, it is not equal to 0. Those constant capital C's are dependent on C4. And when the constant C4 equal to 0, for small r, we get Ricci scalar equal to 0, Ricci tensor squared equal to 0, Ricci Kretschmann equal to 0. But for large r, this is not right. As we see that here, for large r, also this invariant inform us we are not allowed to put C4 equal to 0. But for a small r, no problem. You can put it and recover the BTZ. Okay? So also, what does this mean? This means that we derived a strong black hole for large R. Because as we know that Ricci scalar or Ricci squared, Ricci tensor squared, all of these quantities equal to 0 for BTZ. But in our case, here it is not equal to 0. So this means that for large R, we have a strong black hole. The singularity is strong as R goes to infinity. So we know that this is the form This is the form of f of r, which is the first derivative. Okay? This is in terms of the radial coordinate. So what is the corresponding f of Ricci scalar of this solution? So by making the necessary calculation, we can find that the form of f of r that corresponding to this solution is a polynomial one. As you can see, R squared and so on. And all these constant, these capital C's constant are dependent on C4 and C5. Okay? So for the first modified solution where F, capital F is not equal to 0, we derive a solution that is different from VTZ. We show that it's asymptotic for small r or large r, asymptotically behave as anti-de Sitter or de Sitter depends on the signature, and derive its corresponding F of R asymptotically, of course, which shows that its corresponding F of R behave as a polynomial. So let us repeat all this procedure for the solution where xi not equal to 0. So in that case, as you see that this is the metric for large R, and this is the metric for a small r. Of course, all the capital C's depend on C4, C5, and C3. And as you know that C3 here is the constant that related to the electromagnetic field. So again, this is a very satisfactory solution because as we see that if we got C3, which corresponding to the electromagnetic, and C4, which is corresponding to the modified of F of R equal to 0, in that case, we will discover directly the BTZ. So this solution has no issues for putting C4 or C3 equal to 0 like the previous one. So what is, and as we see that it's the asymptotic behavior behave like anti-de Sitter or de Sitter for large or small. Of course, as we see, this solution is different from the charged solution of BTZ. Okay, we calculate again the invariant of this solution, and as we see that we have issues for small r, that for small r, this gives us a singular solution. But for large r, there is no singularity. It gives a constant one. So, and also we have a strong black hole, which is different from the BTZ, of course. The last class that we will discuss is the general one, where K1 is not equal to 1 and xi is not equal to 0, and F is not equal to constant. In that case, here is the metric for large R and for small r. So here also, as you know that this constant is related to the exponential of F of R. So in that case, for a small r, we can put C6 equal to 0. Here we can't put this constant equal to 0, as you see. But for large r, it is already allowed you to put it equal to 0. For large r, you will discover directly if this constant equal to 0, you will discover the BTZ. But for small r, you are not allowed. So we also calculate the invariant of this solution, and as you see that for large r, we have no problem that the constant C6 equal to 0. We have no problem. In that case, we reproduce the solution of BTZ. But for small r, we are not allowed to put this constant equal to 0. if we repeat the procedure how to calculate the corresponding f of r, we can show that in that case that f of r is a polynomial function. Okay, so we derive the solution, we discuss its asymptotic and show that for the non-charged case, it is not allowed for large R to put the constants that make deviation from BTC to be equal to 0. And for the general case, this case, we discussed it and we show that yeah, before doing the two. Yeah, we show that we are not allowed to put C6 equal to 0 for a small r, as you see here. Here. As you see, we cannot, it is not allowed to put C6 equal to 0. So let us now try to show the behavior of the metric graphically. So where is my there is a filter before? Yeah, here is. So this is the metric that for non-charged case, as we see that this is the form for large R, as we see that we have two horizons for lambda greater than less than 0, and for lambda greater than 0, we have no horizons, which is the blue one. And here is for a small r, as you can see that we have two horizons also for lambda less than 0 and no horizons for lambda greater than 0. This is the behavior of the metric. So let us now show is this solution. All of us know that for any solution within f of r, we should have that f of r and its first derivative and second derivative must be greater than 0. So is this satisfied for our solution? Yes. As you see, this is the behavior of the three solutions that we obtain. This is the behavior of rich scalar, and this is the behavior of f of r for the solution 15 and 16, and this is the behavior of f of r for solution 17 and 18. And this is the behavior of the first derivative, and this is the behavior of the second derivative. So have no issues that their behavior, either f of r or its first and second derivative, to have a positive pattern. Okay? So this is a satisfactory solution. So what about thermodynamics? So let us discuss the thermodynamics of this solution. So as we know that the temperature is defined by this form, where K is the superficial gravity. So if we calculate the temperature for the first solution, which is non-charged solution, I calculated all the thermodynamics quantity to the three cases where F not equal to 0, K1 equal to 1, Xi equal to 0, F not equal to 0, and the Xi not equal to 0, and K1 equal to 1, and the third one is the general case. So this is the temperature of the first solution. So if we plot such a temperature, this is its behavior. So it is increasing without any negative value. If we repeat the calculation, this is the temperature, it decreases for the second solution. And this is the temperature of the general case, where F not equal to constant, Xi not equal to 0, and the K1 not equal to 1. So, and what about entropy? If we calculate the entropy of each solution, so this is the entropy of each one. Okay? And what about this is the value, the behavior of the heat capacity. As we see that the heat capacity is positive, have a positive pattern. So this means that the solution is stable. If the heat capacity has a positive pattern, this means that the solution is stable. This is the plots of the calculations that done through this section. So from the thermodynamics, and in that case, you should know that the entropy within F of R is given by this form, which is different from general relativity, because the effect of the first derivative of F of R is taken into account. So if this is equal to 1, in that case, we return to general relativity. So the entropy in general within modified gravity generally is different from Einstein's theory. So from thermodynamics, the solutions have a good behavior. So up till now, we derived 3 new different BTZ solution within F of R. So let us summarize. This is the physics that I studied in this paper. So let us summarize our result. Here is, we study, in this study, we study black hole solution on 2 plus 1 dimensional within F of R gravity to try to discover a new solution in this aspect. Okay? We have obtained 3 different solutions, charged or non-charged one. So this solution asymptotically behave like de Sitter or anti-de Sitter, depending on the signs of the effective cosmological constant. The invariant of these solutions inform us the constant that make the deviation from the BTZ for large R or for small r, in some cases, are not allowed to be equal to 0. For the present time, I don't have an answer. I don't have answer why this constant must not equal to 0. This means that we cannot, for large R, we can't discover the BTZ, either charged or non-charged, of general relativity. Finally, we study the thermodynamics of this solution and find that it has a good behavior either for temperature, it has a positive behavior for the temperature without any negative behavior like having in general relativity. In spite that we have two horizons. Also, we show that the entropy, in spite that it is effective by the modified gravity that is multiplied by the first derivative of f of r, we show that the entropy behaves in a good manner. The final thing is that we study the heat capacity and show that all the modified solutions that derived in this study have a positive pattern, which means that it is a stable solution. So that's all, and thank you for your. Thank you.
Thank you, Gamal, for your talk. Are there any questions? Caio, maybe you have a question online?
Oh no, it was just applauses.
Okay. Then I have a question.
Yeah.
The constant C6.
Yeah.
Okay. So it cannot be set to 0. Why? Because in the asymptotic expansion, if you set it to 0, then you get a divergence, right?
Yeah.
But what about in the exact case?
In
The exact solution.
exact
Because is this an
yeah, you can put it.
Yeah, this is a series expansion. Usually, there are some, let's say, singular in the sense of exceptional solutions that you have to analyze carefully individually. So if you set C6 equal to 0 at the beginning before any expansion, so do the equations make sense?
Yeah, the question makes sense. Before the expansion, yeah, you are allowed to put it equal to 0. Here is.
Because you have the exact solution with the exponential
Right.
and all that.
Right, here is.
Okay, but here you have the exponential, the EI function, this one that is not well defined. But if you consider the limit when C6 goes to 0, is this giving a sensible result, a meaningful limit, or not?
So for the asymptotic, it depends on the kind of asymptotic. Is it for large R or small r?
Yeah, but the point is that you have C6. The first row, the first line, you don't have any problem. In the second, when C6 goes to 0, these exponentials probably they can generate another. No,
Yeah,
the exponentials go away. The
about-
first time the exponentials cancel each other.
Yeah.
And then you have the denominator has C6 squared, but you have the only problem is the 5r squared and the 5/2r cubed. I mean, it's not easy to
Yes.
understand
Yeah.
what happens to the limit.
Yeah.
But from my experience in other problems, when you have this kind of peculiar behaviors, some value of a constant, you must look at the equations from the origin to see how this constant arises, and then set them to 0 at the right moment. Okay.
Okay.
And then you may get sensible results. So it would be nice to have a look at that solution.
Yeah. Also, it will be nice to study its geodesics.
Yeah, that shouldn't be difficult. And another question is
That should be, this.
shouldn't be difficult.
Yeah.
Yeah.
You see,
Even if you have many terms, well, there are many constants, so in the end you have many
you
options.
can relate, yeah.
But I mean, probably you can consider the leading terms in some regimes and then extract basic information.
Yeah, but the leading term in any asymptote, is it for small r or large r?
Yeah, you need to look at the two.
As the two. So for the two, as you see, especially for this general solution, for the two, you see that the invariance saying that
Yeah, far away the invariants are finite.
yeah, but the metric itself is not allowed you to put C6 equal to 0.
Yeah.
Asymptotically for small.
Yeah, well, this is the expansion,
Yeah,
the perturbative expansion.
yeah,
So
yeah.
this is why for this particular value, you should look at the non-perturbative description of the solution. Okay, and also you have been working with the metric formulation of f of r.
Yeah.
Have you tried with the Palatini formulation?
No,
No? Not yet?
not yet. I didn't make the transformation to transform this solution into Latino
No,
formality.
the equations in the Palatini case are simple.
Yeah, are similar, but I'm not familiar. You see that the tricky thing is that I reduce the system from fourth order to third order. This is the tricky thing, really. So if I put the field equation as it is, it will not be easy to solve the system.
Okay. So any other questions?
You mentioned that you checked this with the BTC solution, right?
With this solution.
But if I remember correctly, the standard case in the BTC case did include rotation. The standard,
BTC rotation.
yeah. The standard, I mean, when you see BTC, the solution includes rotation. Did you try to include rotation?
No, as you see. Yeah, I'm planning to include such a rotation, of course. But as you see, that the terms are not so easy to deal.
No, I know that it's quite scurvy, but
Yeah, but I'm planning to study the rotating term of this solution. Yeah.
because in principle, if the inclusion of rotation in 2.1 dimension is not so complicated in 4 dimensions. I mean,
In 3 dimensions, more.
yeah, exactly. In
Yeah,
three
rotation
dimensions, you just have to include some shift in the metric, and that's all. I mean, the equation are totally a disaster, very obvious, but in practice you can also solve this. In this case, because the standard case charge and charge in this case, you can also resolve. One thing that this case could be more or less the same.
I will try. Yeah, I'm planning to, of course, making the rotating solution of such solution. Yeah.
So I investigated a similar case, quite similar, with a logarithm term, with this additional term with the derivative of the metric with the covariant part. And you can find the solution very, very early, but still it's possible. So I expect that you can also find this easy for you.
Okay. Okay, but as you see that this is capital composed of very complicated of the other constant. So yeah. So this is the reason that I guess that the study of the geodesics will analyze this constant in a clear way. Okay.
Okay, so if there are no more questions, let's thank Gamal again.
Thank you. Thank you.
Okay, and now our next speaker is Professor Peter Dansky. Peter, can you hear us?
Hi there, how are you?
Hello, very good. So, can you share your screen just to check that everything is working?
Sure, just 1 second.
Big button and button. Okay, it's working. So, Peter Dansby is a full professor at the University of Cape Town. He's an expert in theoretical cosmology, and he's a member also of this collaboration, of the I-COOP collaboration with the Cape Town node. And well, today we are happy to have you here, Peter, to see what you have to tell us about F of R theories and dark energy. Feel free to start whenever you want.
Thanks very much. Very sorry I can't be there in person. I would much rather be in Valencia with your nice weather than in rainy Cape Town today. Anyhow, so today I want to talk about some work that I've been doing in collaboration with a number of my students and also a collaborator, Saket Chakraborty. There are 3 papers which I'm going to cover, so you can look them up later on at your leisure. But let's start kind of with a sort of recap of where we are with cosmic concordance, or the lambda CDM model. So we have this incredibly simple model based on the assumption of spatially homogeneous and isotropic background, the Robertson-Walker metric. And it's really quite remarkable just how well this model fits the available data. But it does this at the expense of not knowing what dark energy is. So not really having a proper physical understanding of what the dark sector of the universe is. And as the observations have got better and better over the last few years, various cracks have started to emerge in the foundations of the concordance model. And of course, the most famous of these 2 sort of cracks, so to speak, are the observational tensions in the Hubble constant and also sigma 8. So I'm not going to really talk that much about these tensions today. What I want to focus on for the most part is a way of modeling f of r dark energy in a completely theory-independent way. So we have these observational tensions that I've mentioned, but it's also worth mentioning that we have sort of kinematic sort of tensions as well, so cosmographic degeneracies. So there's a very beautiful relationship that you can derive, which links the evolution of the equation of state parameter for dark energy, WDE, with the cosmographic parameters. So if you remember what the cosmographic parameters are, of course, the most famous of which is the deceleration parameter Q, and then the higher, so this next derivative up is the so-called jerk parameter, and then you keep going higher and higher in derivatives of the scale factor. And of course, from an observational standpoint at the moment, the 2 parameters that we are constraining, in particular with the DESI data, is the deceleration parameter and the jerk parameter. So what you can see from this relationship is that if you choose an exact lambda CDM model where WDE is exactly equal to -1, that implies for a spatially flat model that J is exactly equal to 1. But the converse of this is not true. So if you set J is equal to 1, then there's a whole class of dynamical dark energy models which satisfy that constraint. And that can easily be seen by taking the equation for WDE, setting J is equal to 1, and then finding solutions to this equation. So it's true to say that WDE equal to -1 implies J is 1, but one has to be very careful that when you make measurements of the jerk parameter, take observational data and constrain J, that doesn't necessarily imply that even if you're close to J as 1, that you have an exact lambda CDM model. And I'll touch on that issue a little bit later on towards the end of the talk. So what are the alternatives to lambda CDM? And these can be broadly split into 2 classes. So the first class of alternatives are those that you retain the Robertson-Walker geometry. So you keep the Freeman-Robertson-Walker metric in place. You have then a situation where either dark energy is, standard lambda, is either dynamical, not exactly lambda CDM, it's dynamical dark energy, or you modify gravity. But in both of these cases, the universe is accelerating. So you still have an accelerated late time acceleration, but the dark sector is dynamical. So either a modification of GR or some scalar field, which is modeling the dark energy dynamics. The other alternative is that you throw away the Robertson-Walker geometry, so you get rid of standard Robertson-Walker, and you replace it with, for example, an inhomogeneous metric or some kind of sort of back reaction, nonlinear effect, which gives rise to an effect, well, not really an accelerating universe, because the universe is not accelerating, but basically it tricks you into thinking that the universe is accelerating because you're fitting data to the model and inferring, in this case, that the universe is not accelerating. While in the case of Robertson-Walker, when you fit the Robertson-Walker metric to the data, you infer that the universe is accelerating. So those are the two broad classes of alternatives to lambda CDM. And it kind of brings to the fore a very important point, which was pointed out by myself and Jean-Philippe Uzan and others, that the well-known sort of smoking gun for dynamical dark energy or modified gravity, where the growth factor gamma, so when gamma is 0.55, then you have a lambda CDM model. But the claim is that if you measure gamma to be different from 0.55, that implies that the universe is either has a dynamical dark energy component or you have modified gravity. And what we showed a number of years ago was that this is not strictly true. If, for example, you take a very simple inhomogeneous model, the LTB metric, for example, which has two free functions. So what you can do with that is a rather nice thing, is that you can take data like number counts and the luminosity distance, and you can fit those two free functions in such a way that the background light cone structure is exactly the same as lambda CDM. So from the point of view of observations, there's no way of distinguishing between an LTB metric and a Robertson-Walker metric. However, if you now perturb that model, so if you look at perturbations of LTB to work out what the growth rate is, so what the growth of structure is, then you find values of gamma which are different to 0.55, actually quite significantly different from 0.55. So here's a very nice example where you have to be very careful with using important observational parameters like gamma to tell you something about the physics of the dark universe. So from my point of view, the sort of two really important observations going forward are, first of all, trying to pin down whether or not the Robertson-Walker metric is a good description of the large-scale geometry of the universe, so the so-called cosmological principle or Copernican principle. And this can be tested using redshift drift, where there is a difference in the redshift drift to what you get with an inhomogeneous model and with the standard Robertson-Walker model. But this is an incredibly difficult measurement to make, and typically one would have to wait anything between, I guess, 10 and 20 years to be able to get enough statistical significance in the evidence to support that claim. And the other important parameter, of course, is the equation of state parameter. So if you're able to pin down the cosmological principle, then you're on a good kind of solid ground with regard to testing what kind of dynamical dark energy we have, whether it's modified gravity or whether it's a scalar field, whether it's quintessence, for example. And of course, this can be done, as I mentioned at the start of the talk, through measurements of the higher order cosmographic parameters. So I think going forward, with DESI and with Euclid coming up next year, I think the first data release will be in October. We really have a very exciting prospect of measuring W, trying to constrain W, but of course remembering always that we're assuming that the cosmological principle holds in that case. So we're going to have to wait for some time before we can really pin that down for certainty whether or not the Robertson-Walker metric provides the correct description of the large-scale universe. Okay, so what am I going to focus on today in my talk? So I want to look at various approaches to F of R cosmological modeling. The reason I'm choosing F of R gravity really here is because it's a very relatively simple modification to general relativity. And I would view F of R gravity and other modifications of gravity really as a testing ground for GR. You're really trying to test the limitations of general relativity by extending the sort of gravitational phase space, so to speak, in such a way to test the robustness of general relativity. So I'm going to run through a number of simple examples, and then I'm going to show that one can develop a very nice theory-independent way of describing F of R dark energy by combining methods of dynamical systems and also cosmography. And then at the end of the talk, I'll go back to this point I made about the sort of cosmographic degeneracy between J as 1 and W equal to -1, and talk about models which are very close to lambda CDM and see whether we can, whether that necessarily implies that the equation of state is almost lambda CDM as well. Okay, so very briefly, this is very familiar to most people in the audience. We start with the action where we replace the Ricci scalar with a function of R in these class of theories, and then you end up with a fourth order set of field equations, which you can rearrange in such a way that you have essentially the Einstein tensor on the left-hand side, and then standard matter and an effective curvature fluid, which plays the role of dynamical dark energy. You might be hearing in the background, I don't know whether you hear, there's cheering in the background, that this is due to graduation taking place at the moment. So just excuse the background noise. Right, so when you take a Robertson-Walker metric, so if you take the standard cosmology and you write down the Friedmann equation and the Ray-Choudhury equation for F of R gravity, then you end up with a much more complicated system of differential equations than you do in standard GR. And that means that finding solutions to these equations in general is extremely difficult. So there have been a lot of approaches to tackling this. One approach is to try and use reconstruction. Another one is to use dynamical systems. And a third approach is to use cosmography. So I'm going to be focusing largely on the second two, and then showing you how you can combine them to produce a general theory-independent cosmographic approach to these theories. So just very briefly, the reconstruction method that has sort of been widely very, very popular in the literature over many years. What does one do there? Well, in this case, one takes one pins down the expansion history of the universe, or some property of the expansion history, for example, the scale factor. And then provided you can invert the scale factor, so in other words, write A as a function of the Ricci scalar, then you can convert the Friedmann equation into a differential equation for F of R and solve that equation for the class of theories that give you that background expansion history. So for example, in the case of lambda CDM, when you do that, you get two solutions. One is the trivial solution, which is just GR, and the second solution, the general solution, is a set of hypergeometric functions, which of course are very difficult to deal with. So if you take then that F of R theory, which gives rise to expansion histories which are the same as lambda CDM, then studying those theories using these horrible hypergeometric functions makes life extremely difficult, particularly when you want to do perturbation theory to study large-scale structure. Another very simple example, just to illustrate how you can go about doing these kind of things. So here we have an example where instead of setting the scale factor or setting A of t, which is the previous case, here we instead fix the Hubble parameter, or A dot, the derivative of A, as a function of the scale factor. And in that case, you can also invert to write down a differential equation for f of r. So here we have a model which exhibits cyclic behavior, and you can go ahead and reconstruct the f of r that gives rise to that cyclic evolution in the scale factor. And it turns out to be a second order polynomial in R. Okay, so I mean, this is a rather, not a particularly illuminating approach, because you're limited by the fact that you have to invert the scale factor or invert whatever function you're using, whether it's the Hubble parameter or the deceleration parameter. You've always got to invert that to write things as a function of the Ricci scalar. And you've got to do this on a case-by-case basis. So it's not a very productive way of studying the dynamics of f of r gravity. A much better approach is using dynamical systems. So in this case, we adapt an approach which was developed by people like John Wainwright and written up in a very nice book edited by Wainwright and Ellis. And that provides a very nice way of determining the full phase space of solutions for a given f of r theory of gravity. So in the case of GR, in the case of lambda CDM, for example, this is particularly easy. So here we have a very nice result due to Goliath and Ellis back in 1999, where they were able to write down the cosmological equations in autonomous form by compactifying the phase space by using the Friedmann constraint to identify a normalization parameter d, which allows one to compactify the phase space for the dynamics. So this was a very clever way of unifying, putting together the dynamics of flat, open, and closed models on a single phase portrait. So here we have the phase portrait for all these models. So the left-hand side of the portrait corresponds to expanding solutions. The right-hand side corresponds to contracting solutions. Oh, excuse me, let me go back. Of course, in the center of this phase portrait is the Einstein static solution, which is a saddle point. So orbits will start at F plus in a lambda CDM context and evolve towards the de Sitter solution at late times, which is denoted by ds plus. So that's a nice way of representing the class of solutions that you get using Robertson-Walker metric, standard cold dark matter plus a cosmological constant. So what we did was we adapted this to f of r gravity by doing the same kind of thing. You write down the Friedmann constraint and you identify terms on the left-hand side which give rise to or allow you to construct a normalization which compactifies your phase space. So in this way, you can define a set of variables which give you, a modified density parameter, a parameter Q, just like in the GR case, which splits the phase space into expanding solutions and contracting solutions, and then a set of variables X, Z, and Y, which characterize the modification due to gravity. In particular, X is going to be extremely important in what I will talk about later on. So X really is the variable that properly quantifies the deviation away from general relativity. So when you write down the autonomous dynamical system, you notice something rather unfortunate, and that is that, like in the reconstruction setup, again, you have a situation where you can't completely close the system. You have a term gamma, which remains a function of the Ricci scalar. So again, like the reconstruction scheme, you have to go through, through the analysis on a case-by-case basis. You can't do this in a complete generality. You can't do this for a general f of r. And you're also restricted by the fact that not always are you going to be able to invert this term, the gamma that appears in such a way that you can write the compact dynamical system entirely in autonomous form. So again, you're kind of restricted to, not just, going case by case through, a set of f of r theories, but only certain f of r theories are going to be invertible. So only simple theories are going to allow one to use this approach to do the analysis. But nevertheless, you can do this for, a number of interesting cases. So here we have r plus alpha r to the n. So when n is 2, you have the standard Starobinsky there's modification to gr. And when you do this for r plus alpha to r to the n, you get, you can calculate the fixed points, and you find 3 particularly interesting fixed points. One corresponding to standard matter-dominated phase, which is a saddle point, just like it is in GR. You get late time attractor, which is de Sitter solution. But you also get an early time sort of repeller or late time or early time attractor, which corresponds to power law inflation. So in this case, you can unify, power law inflation with intermediate matter-dominated era during which structure can form, and then you have your late time acceleration, which asymptotically evolves towards the de Sitter solution or the de Sitter attractor. So this is a nice model to study, and it kind of illustrates the power of this technique to analyze at least those classes of f of r theories that you can invert to be able to write down the equations in autonomous form. Okay, so how can we do better than this? Can we, in some sense, avoid this closure condition, this issue that you get with gamma? And it turns out that you can do this by noticing that you can write gamma in terms of the standard dynamical variables, x, y, and v, and also the cosmographic parameters. So and you can do this in a completely general way. There's essentially now you have a way of writing down gamma in such a way that the equations are closed, that you don't need to a priori impose a particular f of r theory of gravity. So essentially the set of equation, or the equations, sort of can be broken up into 2 sets. One describing the gravitational sector, or the evolution of the variables x, y, and v. So that describes the dynamics of the sort of dark energy sector. And then a set of equations which describe the kinematics of the universe, and that's going to come from the cosmographic parameters q, j, and then the higher order terms as well. The snap parameter, and then the next one up will be the look parameter. So when you write down the evolution equations, as I said, you get 2 sets. One which can be broadly characterized as describing gravity. That's the first set. And then the second set corresponds to the cosmography, which is an infinite set of equations. So it's not, it's closed in the sense that you don't need to specify f of r, but you still have a problem in that because your cosmographic series is an infinite series, you have an infinite set of equations for the cosmographic series, Q, J, S, and so on. So you still need to input something to be able to close the system of equations. And you can do this in two ways. You can either do this theoretically by hand, by imposing an expansion history. So you can say, for example, okay, we want to look at the dynamics of F of R gravity in general, but within the context of having an expansion history the same as lambda CDM, or maybe close to lambda CDM. Or, even better, and maybe this might be possible in the future, you use data to constrain Q, J, and S, the cosmographic series, and you try and construct using data what your expansion history is. And then that will pin down what your cosmographic series is and allow you to close your equations for the cosmography. So I think this presents a rather exciting way forward in that, eventually, hopefully the data will be good enough to be able to do that, where you'll be able to pin down your expansion history using data and then constrain the gravitational sector or the dark sector by looking at the dynamics of of these models in general, given the expansion history that you've constructed from data. Okay, so there are two important conditions, of course, that still need to be satisfied. You've got the set of equations, but you still need to have two conditions. One, which gives you the avoidance of ghosts, and the second, the avoidance of Dolkov-Kowarski instabilities. And what this does is it puts a constraint on your phase space. So it puts when you calculate what F prime and F double prime is, you can construct using your dynamical variables and your cosmographic parameters a constraint on the physical region or the allowed physical region of your phase space. And that's that's also a very nice property of this approach, because then what you can do is you can identify orbits in your phase space which satisfy these constraints. So you can determine what the allowed orbits are that give rise to a cosmology which avoids these instabilities. So let's now apply this whole approach to the simplest case that you could look at. So we're going to fix our expansion history, and we're going to fix it to be exactly the same as lambda CDM, but we're going to include spatial curvature as well. So the relationship J is 1 can be generalized to include models which have spatial curvature, either open cosmologies or closed cosmologies. And J is equal to 1 becomes now J is equal to K plus K plus 1, where K is the expansion normalized spatial curvature. And then what you can do is, because you now have pinned down what J is, you've imposed a cosmographic constraint on your expansion history, you can close your full set of equations, but not in such a way that you don't have to specify what F of R is, what your gravitational theory is. And in this case, you end up with two equations which describe your gravitational sector, one describing X, and if you remember what X is, so X is this variable which depends on the second derivative of F divided by the first derivative of F. And so it describes the dynamics of X. Then the density parameter divided by F prime, that's omega, and then an equation for the spatial curvature, which actually leads to an invariant submanifold for K is equal to 0. So you can see the flat models are an invariant submanifold in this general phase space of dynamics. So that's your gravitational sector, and then of course you have your cosmographic series, which now, because you've imposed j is equal to k plus 1 becomes just an equation for the deceleration parameter q. So the series truncates at that level, at the level of q, and you don't need any more information from the higher order cosmographic parameters. So that's your set of dynamical equations. And then what you can do is the standard analysis determining the fixed points and the relationship between these fixed points by studying the orbits in that phase space. So again, you end up with exactly the kind of features you want. You have a transient matter-dominated phase, which is a saddle point. So that's during the phase during which structure forms. Then you have, of course, a late-time future attractor, which represents the de Sitter solution. So those are your fixed points. And then you can plot your phase portrait. So this is a projection. It's a three-dimensional phase portrait in general. So you have to look at just projections of that phase space. But it allows you to that constraint which I wrote down on the phase space, which arises from the conditions for physical viability of f of r gravity. So that divides your phase portrait into two regions, one which is viable and one which is physical. So the purple region is the viable region, and the white, so the region on the right-hand side is the unphysical, unviable region. So now what you can do is you can start in your matter-dominated epoch at P3 or in the neighborhood of P3, and you can evolve your dynamics forward in time and choose orbits which are physically viable. In other words, those orbits which stay in the purple region, but stay close, relatively close to the x equal to 0 line. Remember, x equal to 0 corresponds to GR. So you want a model which is not too different from x is 0 for much of its history. And only in recent times, only in the current epoch, in the dark energy dominated epoch, should we have deviations away from general relativity which manifest themselves as dark energy and accelerate the universe. So now you can basically choose initial conditions in such a way that you get exactly the orbit that you want. So just some examples. So here you can see that the red orbit, so the first orbit here in the diagram, that moves very quickly away from the x equal to 0 line. So that will lead to very significant observational differences from lambda CDM at the perturbative level. So particularly if you look at the growth of structure, you are going to get growth rates and growth factors which are very different from lambda CDM. The green orbit moves away from P3, the matter-dominated saddle point, in such a way that it does stay close to x equal to 0, but the trouble is it moves into the region on the right-hand side, so therefore it's not viable. And that's the same for the orange orbit, that both has a problem in that it moves quickly away from P3 and the x equal to 0 line, and is also non-viable. So the blue orbit, or orbits close to the blue orbit, are the ones that we're looking for. They're the ones that evolve close to x equal to 0 for some of the evolution, and then evolve towards a deceleration parameter which is close to what we measure today in the data. So here is an example, that we constructed of such an orbit. So what you do is you set up your initial conditions. So here we have our initial conditions on x, which is about, the magnitude of x is about 10 to the minus 3. We calculate at our starting point the values of the density parameter and the deceleration parameter. And we can do this by solving, the equations for omega and q in such a way that they match up exactly with what you would expect for lambda CDM. Remember, we've chosen our background expansion history to be lambda CDM, so Q at our initial starting point in phase space should equal to exactly the value of Q that you get for that starting redshift as you would get in lambda CDM. Omega, of course, there's a deviation due to F prime. It's omega matter divided by F prime, so that's not exactly going to be equal to the standard density parameter in lambda CDM. And then you evolve that orbit forward to the present day. So you end up with a Q of, negative 0.55, which is, what you want. And you can calculate what your deviation away from GR is through the value of X. So here we have a value of X, which is 0.226 roughly. So we'll get a sense of what these values mean a little bit later when we look at the growth of structure. So here is a sort of graphical representation of what's going on. So the top left panel is the evolution of the Hubble rate or the Hubble parameter. And of course, that has to be exactly the same as GR, because that's how we've constructed our model as being the same as lambda CDM. And likewise, Q has exactly the right behavior, has the same behavior as lambda CDM. The differences arise in the bottom panel. So on the left-hand side, we've got omega, which is very close to GR at high redshift, at a redshift of 6, where we're setting down our initial conditions, and then evolves away from general relativity as we approach the present day at z equal to 0. And then the bottom right-hand panel, you can see that's the evolution of X as a function of redshift. And again, you can see, we're very close to GR at high redshift, which is what you want. And then as you approach the present epoch, you deviate, you move away from X equal to 0. And that's where the modifications of GR kick in and lead to late time acceleration. And then, of course, you could even go ahead and reconstruct what the gravitational action looks like in this case. So here we have a reconstruction of F prime as a function of the Ricci scalar. F prime of R as a function of redshift, actually, in this plot. So you can see here that for high redshift, F prime is small, very close to 0, which is what you want. You want your early time cosmology to correspond to lambda CDM, and then your late cosmology to deviate away from lambda CDM. And then you can do the full reconstruction of F, and you can see here we have a model which is very close to the linear action that you get for general relativity, and the deviation is plotted on the bottom panel, or the deviation away from general relativity. You can see here, that at low values of R, you have roughly a 10% deviation away from general relativity. Okay, what about the growth of large-scale structure? Can we do this in a way which is also completely theory independent, rather than use a given parameterization for f of R, or use a particular pet theory that you have in the f of R gravitational sector. So these are the fourth order equations for the growth of large scale structure. So delta here is the evolution of your matter fluctuations, and curly R is the evolution of the sort of spatial variations of the Ricci scalar, and that's related to the gravitational potentials phi and psi. So the idea here is to basically take these equations and write them in a way that you can express the coefficients in terms of the cosmography and the dynamical systems variables. But before I do that, it's worth mentioning the various approximations that I used in the study of of perturbations in modified gravity. And of course, these are this is the famous quasi-static approximation. So this can be broken up into two different levels, which we call semi-quasi-static and then full quasi-static. So the semi-quasi-static ignores the time evolution of the potentials relative to the expansion rate. And then the full quasi-static approximation goes one step further and looks at scales, small scales, and that allows you then to reduce the full fourth order set of equations into a rather simple second order differential equation in the non-relativistic limit. So the idea now is to basically write down our equations in terms of cosmography and dynamical systems variables, and we can do this by calculating all the terms in terms of cosmography, which we've done, which you can do for the Ricci scalar and its derivatives, and also f and its derivatives. And then write down, starting with the full set of equations, the full general nonlinear fourth order set of equations, and then progressively go and look at the different approximations. Now, why is that important? Why is that useful? Well, what we can now do with this approach is we can test the rigidity of, the applicability of the various approximations that are used to study the growth of large-scale structure in f of r gravity. So these are the exact equations expressed in terms of redshift, and then we can go and work out the two levels of approximation, the semi-quasi-static and then the full quasi-static approximations. And then we can test, how well these approximations, stand up against the evolution of the full fourth order system of equations. Okay, so again, these equations I've written down here are completely general, so we don't specify what our cosmography is, what our background expansion history is. We can now specialize to our lambda CDM background, so the background that I've described up till now. We can now set J is equal to 1 for a flat, spatially flat background. And then reduce the set of equations down to something where the background is described by a lambda CDM, and we look now at the growth of matter perturbations on that background. And what we're particularly interested in computing is the growth function f and also the growth index gamma. So those are the measurable things that we want to compare with data. So before I get into the actual plots, it's actually worth now just giving you a sort of a qualitative description of what's going on. So here we have two plots. On the right-hand side, we have a plot of the initial value of x. So remember, x is a measure of how far we are away from general relativity in general, and x initial is how far we are away from general relativity at our initial redshift. So here you can see that the smaller x is, if you take x to be of order 10 to the minus 4 initially, then the modes essentially are essentially behaving like they would in general relativity. None of these modes will have had time to enter the f of r regime. So essentially what you're doing is you're making the theory so close to general relativity that you won't actually detect any differences from general relativity when you look at the growth of structure. But the larger you make x, so if you now take x to be 10 to the minus 3, which is what we have taken in our example. so 0.001, then you can see that you are going to start to have modes. So modes which have a K which is greater than about 0.03 will have entered the F of R regime by the present day. Now, on the left-hand side, you have a kind of similar picture where, again, you can pick a scale. So, for example, you pick a scale where K is equal to 0.05. And then you can actually work out what the transition redshift is for that scale. So at what point those scales feel the fifth force, so to speak, and enter the F of R regime. So in that case, when you have K as 0.05, then those scales enter at around a redshift of about 0.07. So, so that gives you a sense of, what scales are going to be impacted by the modification of gravity when one looks at the evolution of the perturbations. Okay, so what are the results that we got? So what we wanted to do was we wanted to compare what we get from the exact solutions. These are the panels on the left-hand side. So the top left-hand panel is the evolution of F, that's the growth function. And the bottom panel is the growth index, gamma. And then on the right-hand side, we've got the semi-quasi-static approximation. And two things you notice straight away is the first thing is that, broadly speaking, if you compare these results with what's been obtained in the literature using particular F of R theories like the Hu and Savicki theory of gravity, they're broadly consistent with what is found in those theories. So typically you get a gamma which is in the close to about 0.4. But the other thing you notice when you look at these plots is that there is a subtle difference between what one finds for the exact solutions and the semi-quasi-static approximation in this case. So you can see there's a variance in gamma. There's a difference in gamma depending on your scale in what you get between the exact solution and the quasi-static approximation. And this gets worse for the full quasi-static approximation. So if one now goes to the full quasi-static approximation, you can see that on redshifts bigger than, say, about 0.2, you start to get significant differences between what you find from the exact solution and what one gets for the full quasi-static approximation. So that indicates that care must be taken when one analyzes data to constrain these models. Ideally, one should be working with the exact solutions, not the quasi-static approximation. And it's particularly big. The difference is particularly big on those scales, so the so-called quasi-linear scales. So for K values between 0.02 and 0.2, these are the scales which are exactly going to be probed by current and future large-scale structure surveys. So it's very important, I think, to be wary of the differences between what one gets using the exact equations and the full quasi-static approximation. Another illustration of this is in looking at the redshift dependence or the growth index. So here we have essentially parameterized gamma. We've essentially done a first order series approximation of gamma, where we just include the linear term in redshift. And we've got plots here of gamma naught and gamma prime, the derivative of gamma. And again, you can see that in the sort of quasi-linear regime, the exact scales that one wants to probe, there are very significant differences between what one gets for the exact solution, which is in red here, when we look at gamma naught, and the semi-quasi-static approximation in green, and also the full quasi-static approximation in blue. And this is, particularly evident at a K value of 0.05. And the same is true for gamma prime. So I think this is, it's very important to be wary of this, that these approximations are great. They work well on very small scales. But if you start to look at larger scales, so, the sort of quasi-linear scales, then there are differences of up to 20% between what one gets between the the full quasi-static approximation and the exact solutions. Okay, so to end this talk, I just want to mention some recent work that we've done on this cosmographic degeneracy that I talked about at the beginning of my talk. So the question we wanted to address here was that we know what happens for an exact lambda CDM model, right? So for an exact lambda CDM model, we have J is equal to 1. So omega, W dark energy is -1, J is equal to exactly 1. So what happens now if we slightly deviate away from an exact lambda CDM expansion history? And we did this in two different ways. So we constructed two models which are close to lambda CDM, parameterized by a parameter epsilon. So the first model, model 1, we've basically taken the lambda CDM scale factor and we've raised it. So we've modified the exponent using this parameter epsilon. And if we do that, we can actually compute what the jerk parameter is exactly in this case. So you can see when epsilon is equal to 0, you have exact lambda CDM. And if we are differing from lambda CDM slightly, then there'll be a slight correction to J in the form of the deceleration parameter 3 epsilon times Q. Model 2, we've done a very straightforward change in the jerk parameter. So in lambda CDM, J is equal to 1 exactly for all redshift. We've now said, okay, let's change J by a small amount. It's not dynamical, so J is just slightly different from 1 at all redshifts. And then what we did was we used the recent DESI results to see whether we could constrain epsilon. So to see whether DESI would give us an epsilon compatible with lambda CDM, right? So if we do live in a lambda CDM model, then the data should kind of tell us that the expansion history is lambda CDM essentially. And what you can see here is that this is far from what we get. If we take the DESI results, for example, DESI plus Pantheon plus, then you get an epsilon which is equal to minus 0.49. So this is substantially, this is not small. This is definitely not small. And this is true for both model 1 and model 2. And if we add CMB data to this, so if we take DESI, CMB, and Pantheon plus, then we get an even bigger value for epsilon. So the data is indicating a model which is very different from lambda CDM and certainly not equal to lambda CDM. And if we now plot the expansion history and the cosmographic parameters, so here we have the Hubble rate for model 1 and model 2. Blue is the green is the exact lambda CDM model. Blue is DESI plus Pentanon and does pretty well at low redshift. So it's pretty close to lambda CDM at low redshift. But at the moment you add CMB data to this, then by a redshift of 0.5, you differ quite substantially from the lambda CDM Hubble rate. And this is similarly true for model 2. If you plot the same kind of thing happens for the deceleration parameter. DESI plus Pentanon plus does okay. You know, it's at low redshift. So the green and blue curves are fairly close to each other at low redshift. But the moment you add CMB data, you get a model which is totally different from lambda CDM. And that's also true for model 2. And then you can compute the jerk parameter, and the same pattern occurs. You know, for DESI plus Pentanon, you have J values which are not too different from 1. They're fairly constant for both model 1 and model 2. But the moment you add CMB data into the mix, you get a jerk parameter which is totally different from what you would expect. And again, you know, for DL, we also get a similar kind of pattern, emerging differences between the different models. And you can then construct what your equation of state parameter looks like. Again, the same thing seems to occur, you know, for redshifts up to 1, you have DESI plus Pentanon plus gives you an almost constant W dark energy, which then becomes phantom beyond a redshift of 1.5. But if you include CMB data, then you end up with a phantom equation of state at much lower redshift. And that's true for both models 1 and model 2. Okay, so just to summarize, so what we've done here is we've used dynamical systems methods and cosmography to construct what we think is a powerful tool to study F of R dark energy in a completely model independent way. And we believe this approach could be extended to a range of different modifications of general relativity, not just F of R. And indeed also, possibly even beyond this to studying general, dynamical dark energy models within the context of GR as well. The results for large-scale structure analysis were broadly consistent with model-dependent studies on small scales, but for quasi-linear scales, we get, differences between the exact solutions and the quasi-static approximation up to around 20%. So this indicates that when doing analysis of large-scale structure, one should be very careful with using these approximations when doing the data analysis. And then finally, we looked at models which are close to lambda CDM and constrained these models using DESI results to indicate that there really is it's highly sensitive. The expansion history is highly sensitive to changes in the cosmography. So one has to be very careful inferring anything useful from cosmography in terms of pinning down, or providing evidence that the expansion history is consistent with lambda CDM. Okay, so I think I'll leave it here and open things up for questions. Thanks very much.
Thank you, Peter. So are there any questions or comments? I was wondering about the extension to other of this approach to other theories, in particular since F of R can be seen as a particular case of scalar tensor theory, like Orlensky. Have anybody tried to implement this approach in the Orlensky family or in some scalar tensor theory?
Certainly, well, yeah, this is something we are, it's on our radar. We are working on this. I would say f of q is the obvious extension that should be relatively easy to do. But more broadly, I think we should try and develop things in this way for general scalar tensor theories, or both in and also dynamical dark energy models in GR. The more we can do things in a model independent way, the better. Because at the end of the day, we want to be in a position where we can use data to constrain the gravitational sector, to tell us, what theories of gravity or what theories of dynamical dark energy are consistent with the data, rather than to do things in the traditional way where we're taking classes of models and then using data to constrain those classes of models.
I see. So since here you are not, since this is some model independent in the sense that you are not specifying the f of r function, so what are the aspects that you can constrain with the data? Are you constraining the matter sector, or?
Yeah, I mean, essentially what we did was we were able to compute for this particular case where the expansion history is lambda CDM, the results that we gave for the growth rate and the growth index, these results here, these are completely general. So they don't depend on a particular choice of F. So all we've done here is we said, okay, the expansion history has to be lambda CDM, but we haven't said what f of r is. We're able to we can reconstruct the theory from the data, so to speak. But what's reassuring here is that we're getting results which are broadly consistent with results that have been published in the literature where they've done this analysis for particular classes of f of r theories, in particular the Huyn-Savicki theories, or the theories which are the designer theories, which have the properties that one wants, to have a accelerating late time expansion history and also an expansion history which is consistent with at high redshift with lambda CDM. So we're getting results which are consistent with that. They all get a gamma, for example, which is broadly close to 0.4. We're also getting 0.4, for our analysis for a broad range of scales. But what we wanted to highlight here was the differences between the exact solution, the exact analysis, and the different approximations that people make. Right. So, and you can see that there is quite a subtle difference between what one gets using the exact solutions and what one gets using the full quasi-static approximation.
Okay. So we have another question here.
Hello, Rolf. So my question is, a couple of years ago, for my master's, I actually also looked into f of r cosmography. And we did actually manage to fit the specific models we were looking at Huyn-Savicki, to the JLA data back then. And we did manage to fit it, but the constraints on the cosmographic parameters themselves, the J parameter, the deceleration, those weren't actually really constrained. The main constraints still came just from Hubble and matter density. So does this actually now finally constrain those better than or is the constraint mostly still related to the others, and this has no big effect.
Well, I mean, the approach is different. I guess in your analysis, what you did was you took a particular F of R theory, right?
Yes.
And then you constrained the cosmography and did you say also the growth rate as well?
I remember we had Q0, Q1, and I think J, if I remember correctly. It was a couple of years ago.
Oh, so this is a model specific analysis. So what we have here is something which is model independent. Okay, so all we've done is we've fixed the cosmography. So in this case, we fixed the cosmography to be the same as lambda CDM, but that not need be the case. We did this as, this is a very simple example. You could take now cosmography, which you could take data, which is constraining cosmography or constraining the expansion history, determine what the cosmographic constraint is, and then redo this analysis to see what that says about the gravitational sector. So in other words, what does that say about the class of F of R theories that are consistent with that particular expansion history? So rather go model by model and then trying to constrain cosmography for that particular model, we'd rather do things the other way around, where we take cosmography and try and constrain the gravitational sector. Because at the end of the day, what we're measuring is cosmography. We're measuring Q and J, and we want to then use that to constrain our, the gravitational sector or the dynamics or the potential of the quintessence field, for example, or whatever dynamical dark energy model you want to look at. So we're trying to do things in a way which is driven more from observations rather than the other way around, where you take a particular theory and then you compute everything and you can then compare to observations for that particular theory.
Okay, yeah, you answered my question. I think it's mainly because we kept everything free, and then it was dominated by the one side and never really constrained the other side. Whereas if you split it up, firstly, if you have data, you're fixing the one and then constrain the other. Okay, so I understand. Thank you.
Thanks.
Okay, is there any other question or comment? No, if not, then thank you, Peter, again.
Thank you very much, and good luck with the rest of the meeting.
Thank you. Thank you so much. Okay, so our next speaker is Caio. Caio.
Hi, everyone.
You can share the screen.
Okay.
Aí quer que fique listado os igual.
Share my screen. Okay. I hope you can all see my presentation now.
Yeah, we can see the presentation, maybe full screen now, much better. Okay, so Caio is now a master student at the Federal University of Ceará in Fortaleza. And he's going to present an original idea about a new kind of stars. Okay, so Caio, go ahead.
Okay, thank you, Professor. Well, Professor Gonzalo already introduced me. This is a joint project advised by Professor Gonzalo and with a collaborator from São Paulo, who's a PhD student, Nicholas Aguiar. So I hope at the end of the talk you can all understand this beautiful picture. So we all know that in Newtonian theory, we have that the gravitational field is pretty well described by this Poisson equation. But, well, what you have there is that masses and densities will give description about the gravitational field, whereas general relativity we'll also care about pressure, stresses, and energy momentum flows, which is a much more complicated equation. And well, we know that in general relativity, we like to simplify some things, and sometimes we're interested in static and spherical symmetric solutions. And that reduces the Einstein's equations to the TOV equations, which are the Tolman-Oppenheimer-Volkoff equations, which is a pretty simple set of equations. I don't know if this right here isn't okay. No, I think it's better. Okay. So you have the TOV equations, and to solve them, it's pretty simple. You pick a mass profile, a density profile, and then you have a solution for your Einstein's equations, in which you have the PR as the radial pressure, and you have these other P right here, this orthonormal P right here, as the transversal pressures. But we only will care about the isotropic case, right? So, well, a model that most people might be more used to, it's the model of the Sitter spacetime. And the Sitter spacetime, what you have is you have an equation of state, which is P equals minus rho, and we all know that describes a cosmological solution. It's one of the maximally symmetric spacetimes, and of course, this has 10 Killing vector fields. And well, a known solution first introduced by Matsuda and Mottola in the early 2000s is to build a star out of this. So you have the Israel junction conditions, you match the solution with an external fluid envelope, and then you match this to an external Schwarzschild spacetime. Doing this, you build what we call a gravitational vacuum star, or per se a gravastar. And however, this we think that to have this, it's too much symmetric. We don't like things that beautiful. Nature sometimes might not be that simple. So we have something different. If you pick a different solution from the 12 equations in particular, where you have a fluid, a denseless fluid, and massless as well, we have what we're calling the platypus spacetime, in which the solution here is that you have a pressure that follows this pressure profile, and the metric follows like this. And well, we can see that as non-singular, the pressure is only positive always, and it's spatially flat. So it has some special nice features. And well, that's what we are going to talk about. And because general relativity has energy conditions, which will probe some solutions because of causality and etc. We know that the Sitter solution, because you have a cosmological constant with negative pressures and so on, it breaks down all the energy conditions, so it doesn't obey any of the energy conditions. However, the platypus spacetime, or what we call later the platypus stars, only violates the dominant energy condition. And well, if you want to introduce the minimum of less physics and be a bit more conservative, it's better to violate just one rather than 4 of them. So this is metric. It's pretty simple, as we saw. And because it's spherically symmetric, we have energy and angular momentum as conserved quantities, and we can talk about geodesic motion in this space-time. And what's different, it's a subtlety that we have here. It's because sometimes, well, you all saw Anderson talk yesterday, and I think he might have talked about geodesics and so on. And sometimes, or most of the times, the total energy of on this equation 7 is decoupled from the potential. So you usually have on the right-hand side of this equation 7, instead of 0, you have the total energy. However, due to structure of the platypus, they are kind of coupled, and you get you get this form. It's worth just mention that this RP is just a natural scale length that happens in this space-time. So we can write it from the metric. So we'll analyze the geodesics in this, and if we set this kappa in equation 8 equal to 0, it will represent new geodesics, light rays, and we'll set it to -1, it will represent time-like motion. So we wish to find what are the circular orbits, the critical points of this potential. And well, what is the equivalent of the photon ring here, the light ring, photon sphere, whatever you want to call it, is exactly this natural length that we have in this space-time, what we call RP, or the platypus radius. And the energy is given like so. We can rewrite this in terms of the impact parameter, of course, which is defined as the ratio between angular momentum and energy of photons. And well, the critical impact parameter for this point, for the photon ring, is this. And what's funny about this is that, differently from the Schwarzschild spacetime, we know that in Schwarzschild the photon ring is an unstable circular orbit. However, for the platypus is completely stable, which is a nice feature. So we can also see that in the platypus space-time, the new rays, the light rays follow circular orbits always. So what I mean is that they are always stable. So every new ray, if you have a new ray and you push into this space-time, then what you have is a light ray that will bounce between these two radius and this equation 12. And that can be seen in this equation, in this graph right here. Where what this graph tells us is that we have a constraint on the accessible regions of the space-time by the photons in it. So the photons cannot access the full space-time because they are constrained in their orbits. They can only access this colored region right here. Okay. And well, an evidence about this, we can make this phase space plot on the no rays, which is a pretty nice picture. However, we can clearly see that the photon ring, which is this point right here in the x-axis setting to 1, it's a fixed point. And well, the other points that are going to the origin are new rays with 0 angular momentum. So they are radio new geodesics. Okay, we can talk about also about the time-like geodesics. And well, time-like geodesics will have also a nice feature, because in Schwarzschild spacetime, time-like geodesics have innermost circular orbit, which is at 6m. However, in the platypus, what the time-like geodesics have are an OSCO, so outermost circular orbit, because they are also stable orbits, so they also form always stable orbits. However, as you increase the angular momentum of this time-like geodesics, they approach the photon ring. So and the photon ring always have a radius much larger than this time-like orbits. So that's also a nice feature that happens in the platypus. Okay, and as I said before, it's a regular solution. You can calculate the Ricci scalar, for example, and the Ricci scalar has this form. And because the pressure, it's always positive, the radius is always positive, thus the Ricci scalar is always positive as well. However, we also analyze the negative pressure cases. And well, if you want negative pressures, you end up introducing a new natural scale length, which is this RA, which we call the anti-platypus solution, and you can build and have some physics around it, although we will not talk much about it. And well, because the platypus space-time is spatially flat, embedding diagrams that are mostly famous in scientific communications is not a really great tool for it. But we'll talk more about it. And well, for calculations, you can show that the value tensor isn't identical to zero, which is mean that the space-time is locally conformal to Minkowski, or locally conformal to a subregion of the Einstein static universe. And from this, we can start talking about the causal structure of this space-time, because of this property, we can conclude that photons in this space-time actually kind of only see Minkowski. So yeah, and we can draw the Primrose diagrams for the diagram for this space-time, and looks much similar to the anti-de Sitter space-time. We have the structure where I plus and I minus are the future and past time-like regions, and scribe is the space-like and new infinity, and R0 is origin, of course. It's worth to mention that any new ray in this space-time that goes from the origin to scribe takes infinite amount of time to get there, which is okay since our solution is not asymptotically flat, and it's not asymptotically Minkowski. And what we can talk about now, notions of mass, because this space-time has this weird property where its local chunks of mass are zero, and it's also denseless. You could ask, like, if you calculate the Komar mass, the notion of a Komar mass in this, what would you get? And well, the answer is that you get this expression right here. So the mass kind of diverges. And this is a question that we've spent months trying to answer, actually. And it's not that simple, because what you have when you are trying to calculate these notions of global mass in a space-time is that you're always calculating them with respect to another space-time. So the Komar notion, for example, the usual Komar notion calculates the global mass of a space-time with respect to Minkowski. And that's the reason why the Komar mass and the platypus diverges. However, you have other notions of mass. For example, you have the Komar anti-de Sitter notion of mass, which allows you to calculate, for example, the global mass in a Schwarzschild anti-de Sitter spacetime. So it's if you just take the Komar mass notion, the usual notion in the Schwarzschild anti-de Sitter spacetime, you get this divergence as well. However, if you use the Schwarzschild, the Komar anti-de Sitter notion, this expression right here gets it becomes regular. So we can build out of this a notion of a Komar platypus definition, and you could build a Schwarzschild platypus spacetime, a Schwarzschild platypus solution, for example. And well, of course we can talk about quasi-local motions in this space-time, because you can always pick a finite sphere and pick the mass in that regions, but of course that will end up being zero. You'll not get much information out of it. Okay, so I'm sorry if I'm being too fast. I'm really worried about time and questions. So we can start talking just like for the Gravistar case. We can start talking about building a star out of the platypus solution. We pick basically the same procedure. Pick the platypus solution, an external fluid envelope with it. And the outer region is, of course, the Schwarzschild spacetime. And now we can talk about the bending diagrams for this. If we plot the bending diagrams for a certain capacity, which is the ratio between the mass and the radius for a given star. For example, this is a quarter. Then the Schwarzschild star, which is simply a star of constant positive density, we get this picture on the left side. However, for the platypus, we get this one on the right, and we can see the difference here, which is because the nucleus of the platypus has zero mass. And because it has zero mass and it's spatially flat, and the embedding diagrams only capture information about the spatial part of the metric and its mass, then we get this flat region in the middle, and as you go to outer regions, the curvature on the spatial part start to play a role in this. So we get this nice configuration. And well, we know that stars in general relativity are known to obey a theorem, which is the theorem of the Book-Down limit, which states that no capacity can go beyond this ratio of 4/9, or it will end up collapsing into a black hole. So a natural question to ask is, what happens about the Book-Down limit for platypus stars? Because gravitar stars, for example, they violate this limit as well. So does platypus care about that? Well, we can build, we can check this. And well, for a platypus star, if you build a continuous model, what we get is we get this regularization. So for example, this orange line, it's a Schwarzschild star, homogeneous Schwarzschild star, and this blue line right here, it's the platypus. So we can see that when it starts reaching the capacity of the Book-Down capacity, the 4/9 capacity, it explodes, which means that it collapses because the pressure starts to go to infinity. However, the platypus, it's regular. So the platypus can go beyond the Book-Down limit. However, its capacity is not that high. We can see that the capacity goes close to 0.49. However, it does not get that, and we do not achieve a CLIFO, which is a clean photosphere compact object. So well, that's it. And it's worth mentioning that we are always here trying to preserve the positiveness of the pressure. We don't want things with negative pressure. We can go beyond this, of course. We can start talking about the thin shell model. So we've introduced the thin shell in the star model. So introduce some discontinuity in the model. We can go beyond that. And when we do this, we get these two nice graphs. So what happens is the outer radius, which is the radius of the whole star, when it reaches when the radius of the nucleus reaches these outer radius, so the star is basically made out of its own nucleus, then the capacity gets arbitrarily close to that of a black hole. But of course, if it reaches exactly one of the two, which is the capacity of a black hole, it collapses. However, it can get arbitrarily close, which is an astonishing result. So platypus stars might be a well-suited candidate for black hole mimickers. And because it's a horizonless and non-singular object, it might have its advantages when compared to a black hole. We don't need to worry about information paradox or singularities, event horizon, and so on because of these configurations. Of course, there's much to explore in this, but well, Thank you very much for having me, and I'm open to questions.
Thank you, Caio. So, any questions from the audience? Let me see. Well, I can ask questions, but I already know the answer, probably. So, if you don't mind, as if we are a bit late, we're behind the schedule. Maybe we can, if there are no questions in the audience, so we can just thank you, Caio, again.
Thank you.
Thank you so much. Okay, and now we have another speaker. Now this is physical speaker. So we are a bit late. Just information for Marco Aurelio that is online. So your talk will be slightly delayed. Okay, please.
If he wants to go first,
Don't fine.
I can talk last.
As you prefer. So,
Okay.
Marco, maybe if you want to speak now, we can start.
Yeah, sure, no problem. Just
Okay, so
give
let's do that.
me,
Yeah. Okay, yes.
just give me a minute, please. I will change my connection to one better.
Okay. Very good. So, Caio is still sharing the governor. It disappeared. Okay.
So, are you hearing me well?
Yeah, we can hear
alright.
you.
Okay.
Okay,
Okay,
so let me introduce you. You can start sharing the screen. Let me check if everything works. And just to introduce him, so Marco Aurelio did his PhD at the Federal University of Pará in Belém, Brazil. And he's currently, you have a professorship position, right? You are, what's the name of that?
Yes, as a temporary professor.
Temporary professor, exactly. In Pará, right? In Belém?
Yes.
Okay. So, and he accepted my invitation to this workshop. And the plan is to speak about causality and stability in theories governed by nonlinear theories of electrodynamics. Okay. So you can start whenever you want.
All right then. So thank you, Professor Gonzalo, for the nice introduction. So, well, my name is Marco Aurelio, and Professor Gonzalo already introduced me. So I'm going to talk today about causality and stability in geometries associated by nonlinear natural dynamics, which is a work that we have published recently and in collaboration with Haroldo from the Federal University of Maranhão, Pedro Cunha and Professor Carlos Herdeiro from Aveiro in Portugal, and Professor Crispino, which is he from the Federal University of Pará. So I have organized my talk essentially in this way. So we start with a brief introduction about nonlinear natural dynamics. I will discuss the main ideas of such a theory applied to black hole physics. Then we will discuss the criterion for causality, how we define causality in such spacetime, but we will start firstly with linear electrodynamics. Then we will discuss the motion of photons in nonlinear natural dynamics. And after that, two of the theorems that we have proved, which is the rho reversal theorem and the causality stability theorem. And finally, the concluding thoughts. So let's start with the nonlinear natural dynamics in a nutshell to just review what is this theory and how we do apply it to black hole physics. So one of the best ways to introduce nonlinear natural dynamics is start with linear natural dynamics in a flat space-time. So this is the action associated with linear natural dynamics with Maxwell's theory in a flat space-time. So G is the determinant of the metric tensor and F is the Maxwell scalar. By extremizing this action, we can obtain the Maxwell's equations as given by this set of equations here. And it's important to point out that this setup is consistent with the Maxwell's equations in the absence of charges and currents. So we are not considering any kind of current or charge particle. This is Maxwell's, this is essentially Maxwell's theory in vacuum. So we know that the classical electrodynamics has some problems, especially associated with in the strong field regime or for very small distance. And in this sense, the main idea behind nonlinear electrodynamics is an attempt to go beyond the linear level of the Maxwell's equations, trying to solve some of these problems. And a strategy that we use to do that is basically change the Maxwell scalar for a function of the Maxwell scalar. So now we replace this action by this one here. And of course, we're still working in the flat space-time metric just to have an insight about a glimpse of what is the theory. So now we have replaced the action associated with the Maxwell's equation for a new action where instead of the Maxwell scalar, we have the function of the Maxwell scalar. And of course, this is still a flat space-time and this is still vacuum. And by extremizing this action, we obtain this set of equations here. And we can see that even in vacuum, the self-interactions of the nonlinear electromagnetic fields in a very strong regime, they produce an effective charge density and an effective current. So it's like the main idea here is that the self-interactions of the electromagnetic field affects the motion. So we can now move to the case where we are working with curved space-time. So in this situation, we have this action here. So this is basically the Reed scalar associated with the Einstein-Hilbert action plus the term associated with nonlinear electrodynamics. So the idea here is to obtain black hole solutions in this configuration here. So by extremizing this action, you can obtain the Maxwell's equations, but now written in a very compact form, the more elegant form. So we have they given in this equation 6 here. So in this equation here, nabla mu, f mu, where f mu is the Faraday tensor, we can see that the conservation of the Faraday tensor leads to 4 pi times an effective current. And this is a very important result because here we are working in principle, we are not considering any charged particles or any interaction with the environment. So in principle, we are dealing in the case where we have the absence of charges and currents. And even by doing so, we have again this effective current that we have seen this in the flat space-time, but this also occurs in the curved space-time. And it's precisely this effective current term, which is given by this expression here, equation 7, that affects the motion, for instance, of photons. So in nonlinear electrodynamics, photons will follow new geodesics of an effective metric, and we will discuss this later. So the field equations are given by the equation 8, and to obtain black hole solutions, we just need to follow a recipe. So we need to suppose a space-time background. This space-time background could be a spherical symmetric space-time or a rotating space-time. We need to choose a net source. So we have to specify the form of this Lagrangian density here to solve the field equations in order to obtain black hole solutions. And finally, we can solve the field equations to obtain the corresponding black hole solution. So now that we have quickly introduced what is nonlinear electrodynamics and how we obtain black hole solutions in this context, we can move to the criterion for causality. And this is a very important aspect of our work, because let's first look to the Maxwell's case. Let's first consider the geodesics like massless particles or massive particles, but not charged particles, of course. So when we consider geodesics in linear electrodynamics and the Maxwell's theory, like Heisenaustrian black hole, for instance, we will see that in the left pane, in the left side of the equation 9, we have the norm of the free velocity, which is given by x dot. In the right hand side of this equation, we have the norm of the full momentum. And what we observe in electrodynamics is that when we work with photons, for instance, or massive particles as well, we observe that the norm of the full velocity is parallel to the norm of the full momentum. And what this means that if you have a time-like, if you have a full velocity with a time-like norm, it implies that the norm of the full momentum will also be time-like, and vice versa. So if you have a space-like norm for the full velocity, we will necessarily have a space-like norm for the full momentum. And of course, this applies, for instance, this applies only for neutral particles, because if you want to go beyond that, if you consider, for instance, charged particles, we will see that the full momentum and the full velocity, they are related by equation 10. And in this case, this is kind of telling us that P mu and that the full momentum and the full velocity they not need to be parallel, and they almost need not match in sign, so they are not parallel. So you can have, for instance, a situation where you have a time-like full norm for the full velocity, but a space-like norm for the full momentum when we consider charged particles in linear electrodynamics. But when we work with neutral particles like photons or massive particles, the norm of the full velocity is parallel to the norm of the full momentum. And an example of situation where we have, considering, of course, charged particles in electrodynamics, where we have a time-like norm for the full velocity and a space-like norm for the full momentum, is the textbook Larmor problem. In this problem in particular, you can show that the norm of the full velocity is time-like, but the norm of the full momentum can be made space-like. And this happens because if you look to the equation 10, we have this contribution here, which is the product between the charge of the particle and the components of the full vector, so of the full potential vector. And this allows us we have this kind of situations when we work with charged particles in linear electrodynamics. And the question is very simple, but does that also extend to nonlinear electrodynamics? So this criterion for causality look to the norm of the full velocity or just to the norm of the full momentum when we work with photons. This criterion holds in nonlinear electrodynamics, and this is what we want to answer in this presentation. So let's move to the motion of photons in nonlinear electrodynamics. So I showed to you in the beginning of the presentation that the self-interactions of the nonlinear electromagnetic fields in nonlinear electrodynamics introduce an effective current tensor. And this effective current tensor affects the motion of photons in such a way that in nonlinear electrodynamics, photons follow no geodesics of an effective metric, which is given by this equation here, where G bar is the effective metric tensor, and G is the standard metric or space-time metric. The space-time is the metric of the space-time itself. But it's important to note that in nonlinear electrodynamics, photons follow no geodesics of the effective metric tensor, this equation here. But massless particles with nature other than electromagnetic will follow no geodesics according to G mu. So if you use, so we are not going to suppose any model right now. We just have this framework of nonlinear electrodynamics minimally coupled to the Einstein's theory. And by doing that, we can show that using, of course, the Hamilton's equations, that the full momentum of photons in nonlinear electrodynamics are related with the full velocity by this expression here. So this is very similar to charged particles in linear electrodynamics. And this equation is telling us, of course, let me point out this edge tensor here. It's just the contraction of the Faraday tensor. So the equation 12 is telling us that the full momentum of photons in nonlinear electrodynamics are not necessarily parallel to the full velocity of photons, because we have this additional term, which can be made, for instance, positive or negative, and changed the sign of the norm. To have a better idea of what is going on here, we can compute the norm of the full momentum in such a way that we obtain equation 14, and we can also compute the norm of the full velocity and we obtain equation 15. So notice that in the right-hand side of the equation 15, the first term is precisely the norm of the full momentum. So this means that the norm of the full momentum of photons in linear natural dynamics is not parallel to the norm of the full velocity. So you can have situations where the norm, where we have casual motion, but the norm of the full momentum is space-like, for instance. And to see if this is actually possible, we need to start to consider some models. And to consider some models, as I have shown before, we need to follow a recipe. And the first item of the recipe is to consider a space-time. So for simplicity, we will consider a static and spherically symmetric space-time. So G mu, which is the space-time metric, is given by this static and spherically symmetric space-time, and f of r depends on the field equations, but I decided to not put the equations here because this is not actually necessary. But what is actually important to have in mind is that in our work we have considered only magnetically charged black holes to support our results. We have not worked with electrically charged ones, but this is just a choice. We could do this as well. So we have considered more models in the paper, but here we restrict the analysis to only 5 models. So we have considered Bardeen, Bernikov. He should be Hayward instead of Bardeen. We have considered also Bornfield and Ole Heisenberg, which are basically standard models of nonlinear natural dynamics that we have in literature. So now we can move to the first theorem. So if you consider magnetically charged structures, we have this set of equations given by equation 17. So the first equation is the norm of the full moment of the full velocity. We have not considered any model by now. It's just the general setup. We're gonna use the models to test our results to see if they are correct or not. And we have this equation for the full momentum of photons. So we have these 2 equations. The first one is for the full velocity, and the second one is for the full momentum. And of course, keep in mind this is for magnetically charged structures. So basically, magnetically charged space-times. And J is the angular momentum, right? So it's important to emphasize that the Maxwell theory is recovery for weak fields if the conditions given by equation 18 are true in the context that we are in the far field. So if in the far field this holds, it means that the model that we are choosing to work with, it will behave as the Maxwell theory in the weak field limit. An example is the Bornfield model, is the Bronikov model, and examples of where this doesn't happen is the case of Bardeen and Hayward. So if you take the ratio between these 2 equations here and apply this condition, we obtain that far from the source, the norm of the full velocity of photons in nonlinear natural dynamics is approximately, in the first order of approximation, equals to minus the norm of the full momentum. And this is telling us that in nonlinear natural dynamics, the norm of the full velocity of photons and the norm of the full velocity of the full momentum of photons, they have opposite character. So if you have a time-like norm for the full velocity, for the full velocity of photons, this will necessarily imply that you have a space-like norm for the full momentum of photons. And so to summarize that, it means that, for instance, if you have baryonic particles, and baryonic particles are those that where the norm of the full momentum is less than 0. So you have so in this case, so if you have baryonic particles, these baryonic particles, they necessarily must be superluminal in nonlinear natural dynamics because the norm of the full velocity must be greater than 0. We call this result given by equation 19. So, and very interestingly, if you have tachyonic particle for which the norm of the full momentum is greater than 0, this tachyonic particle will necessarily be subluminal in nonlinear natural dynamics because the norm of the full velocity will be smaller than 0. It will be time-like. So To summarize the results in nonlinear electrodynamics, if you have a space-like norm for the full velocity, you will have necessarily a time-like norm for the full momentum. So these results lead us to the following theorem that we have called of row reversal theorem. Let L of F be a net model admitting a Maxwell weak field limit, minimally coupled to Einstein's gravity. For static and spherically symmetric, magnetically charged associate spacetimes, the first order deviation from the Maxwell limit makes photon motion tachyonic and subluminal, or baryonic and subluminal with respect to the spacetime metric. So the key idea is basically the following one. You put an observer in the spacetime metric and ask him how he perceived the motion of photons, and he will notice this motion as tachyonic and subluminal or baryonic and subluminal, as long as we require that the model satisfy correspondence with Maxwell's theory and the weak field limit. So we can move on now to the second theorem, which is the theorem associated with the causality and the stability of the space-time. So the question is, could these results be related to the stability of black holes in nonlinear electrodynamics? So let's quickly discuss the conditions for linear stability and electromagnetic and gravitational perturbations in nonlinear electrodynamics. These sub-conditions are given by the conditions in equation 20. So where capital phi is given by this expression. So if the space-time satisfy all these sub-conditions given by equation 12, given by equation 20, it means that the space-time is stable. But I want you to keep focus in two sub-conditions here. The second one, which is the first derivative of the Lagrangian density with respect to the Maxwell scalar, and the third one, which is capital phi greater than 0. If you look to the third sub-condition, and compare it with our result for the norm of the full velocity, we will see that if you require that the space-time is stable, then capital phi must be greater than 0. And the sign of the norm of the full velocity will be determined only by the sign of the second derivative of the Lagrangian density. And similarly, if we require again that the space-time is stable, then this sub-condition here is greater than 0, and the sign of the norm of the full momentum of photons in nonlinear electrodynamics will be determined solely by the sign of the second order derivative. And this means the following thing. This led us to the following theorem. Let L of F be a net model minimally coupled to Einstein's gravity, a static and spherically symmetric, magnetically charged, linear stable black hole under electromagnetic and gravitational perturbation is casual if the second order derivative of the Lagrangian density is smaller than 0, and is casual if this second order derivative is greater than 0. And of course, due to the previous theorem, in the casual case, photons are tachyonic or null, or in the acacial case, they are baryonic or null. So basically, the criterion for causality in nonlinear electrodynamics when we work with photons lies on the norm of the full velocity, not in the norm of the full momentum. And to show that this is actually the truth, we analyze some concrete case. So here we have 5 models of nonlinear electrodynamics: Bardeen, Bonifier, Bronikov, Ollie Heisenberg, and Hayward. So this is the second order derivative of the Lagrangian density, and you can see that for Bardeen and Hayward, they are mixed. They can have seen positive and negative values. So they are not casual, and you can see that they actually violate the dominant energy condition, which is associated with the causality of the space-time. But for Bonifier, Bronikov, and Ollie Heisenberg, this term here is negative, what indicates that the space-time is casual, as we show by our results. And if you compute the dominant energy condition, we will see that the space-time is actually casual. So what is the takeaway? So going to the concluding thoughts now. The takeaway message is basically following one. Photons follow null geodesics of an effective geometry, of an effective metric. And you can review some imprints of nonlinear electrodynamics in black hole physics by investigating the motion of photons. And here in particular, we have derived theorems bounding causality and stability in such spacetime. So basically, we have seen that if you require that the model must satisfy the correspondence with Maxwell's theory at infinity, the motion of photons must be the norm of the full velocity and the norm of the full moment, they have opposite current. So we have tachyonic and subluminal. The tachyonic particles are subluminal, but the baryonic particles must be superluminal. And we have also obtained a theorem associated with the stability of the space-time. So essentially, the second order derivative of the Lagrangian density with respect to the Maxwell scalar determines if the space-time is causal or not, if you assume that they are stable. Space-time is stable. So as future perspective, we want to explore rotating geometries to go beyond the spherically symmetric case. We also want to consider general Lagrangian density. So instead of here, we have considered a model of the linear dynamics, a framework actually, where the Lagrangian density depends only on the Maxwell scalar. And we can actually go further than that. I consider that the Lagrangian density also depends on the second scalar, which is the G scalar, which is basically the scalar product between the electric and magnetic fields. And of course, keep exploring the limits of nonlinear electrodynamics in black hole physics, but not only in black hole physics. We can also try to better understand the role gauged by nonlinear electrodynamics in alternative theories of gravity, and also black mountains, wormhole geometries, and other kinds of compacts of objects that we have potentially in nature. So these are my concluding thoughts. Thank you all. Any questions or comments?
Thank you, Marco, for your talk. Any questions?
Did you try? Did you try to use the same idea using just the invariant G, not the combination, just L of G?
Not really, because in general, when we obtain these black hole solutions, what happens that we choose the space-time to be magnetically charged or electrically charged. The scalar G is essentially the scalar product between the electric and the magnetic field. So when we assume a particular model of nonlinear electrodynamics that depends only of the electric or of the magnetic charge, these scalar vanish. So in order to properly consider the scalar G, we need to consider both of them, the scalar F and the scalar G. But in our work, we have considering only the Maxwell scalar, the scalar F.
Okay. And now I have another question. From an observational perspective, what should we expect in these cases, if it is superluminal or subluminal? How could we see the imprints of these effects in observations, say, of black hole shadow?
Oh, that's a very, very interesting question. So in my point of view, what we have observed so far is that we have some change in the pattern of the shadows, but I do expect more interesting results when we analyze, for instance, the gravitational redshift or the kinematic redshift. So essentially, the path of the light will change. So we also expect some very interesting results in this sense. But concerning the shadows, the shape of the shadows, so far what we have observed is the shape of it is kind of very similar to the standard results in the literature, like Heisenberg and etc. What we actually do note is that we can have situations where, due to this behavior in nonlinear electrodynamics, we have the existence of a full force term, and this full force term is associated with that full current, and this full force can actually, especially in the case where we have superluminal photons, it helps to the particle to be more absorbed by the black hole. So this affects the size of the shadows, and this is something that is is interesting to investigate as well.
Okay, thank you. So any other question, comment? Nothing here. So thanks a lot, Marco, for your talk.
Thank you. So,
Okay, so now we are approaching the end of this workshop with our last talk.
I started and ended.
Yeah, you.
Let's connect that. And probably also this. Yeah, because to pass the slides. And now, yeah, have you connected?
And also the video. Polygon. Yeah. Yeah, it's already. Yeah, good. Okay, so you already know Renier is going to speak about another code, right?
Yeah.
Yeah, as I told you, he's an expert in coding. He's presenting another code. So,
Okay.
go ahead.
Yes, I get to open and close the thing. So now I'm going to talk about Cosmology, which is actually my own code. I've written it. It started actually back in my master's, but it only gained traction this year due to Shamble actually. So Shamble kept bothering me to use my code. And it's like, I don't understand this and this. So I was just like, okay, I'm going to write it better from the start. So we have all seen this in countless papers. I'm just using here one as an example, where people take a modified gravity model or whatever, kind of how Prof. Dunsby did it earlier, give it, they explain what it is, and then they give the probability distribution of this and the base fit values. And then you can see, okay, this values fit. So because or look similar to the lambda CDM model, so therefore this model works based on observation. In this particular one, all the way back, they were still using JLA, the old SDS, SPLA, and CC. But so why I chose this particular paper? My master's actually started with this paper, and I also wanted to fit models. Also, F of R, so it was a very good paper to follow. But then we realized, well, we actually don't know what procedure they did to get to that. Now, it's straightforward now. Most of us know it's MCMC models. So just background on MCMC. But okay, it started 1950s. First one was developed by Metropolis, 1953, and it was to compute the equation of state of liquid. Later, Hastings made a generalization. But the main goal of these is to construct a chain that basically a stochastic process where each state, the current one, is only dependent on the previous version in the algorithm. It doesn't care about anything else in the entire space. And then as the chain evolves, as it keeps moving forward, it starts to mimic a specific target distribution. Now, from a stats point of view, it kind of works like this. You have your initialization, a value, this can be completely random, or if there has been observations that can give you an indication where to start, you can use this. And then you do a proposal of a new stop, a new position, and it then compares the likelihood of that new value, that new base fit, compared to the previous one, and then it computes a acceptance probability. If the new one has a better likelihood, it automatically accepts it. If it has not a better likelihood, it doesn't fully reject it. It then becomes a game of chance. So it adds in a random number at which it compares to, and if this less likely value is actually better than the random number, it still gets accepted. The reason for this is due to the fact, let's say we have a base fit between this and this point. Here you have a small local minimum in the potential, and here you have the actual base value. If, for instance, your MCMC starts on this side and it falls into that local minimum, if there's no way of getting out, like on this where there's a less likelihood chance, it will be forever stuck in that smaller likelihood. But if there's a mutation where a less likelihood value can come, it can get out of that potential and searches further until it might get to a better one, and then kind of tell his other friends like, go, I have a better option. So mutations are necessary for this to avoid such falling into pits. Okay. Most people, it's common to use a symmetric distribution, a Gaussian. That's why even the newspaper did. And then this actually just reduces back to the original metropolis. Now, the other one, the step size, is basically, this is the tuning part. Each type of MCMC simulation needs to be tuned to some way. People use different ways of tuning it. And the idea is, let's say, okay, again, you have your parameter space, here's your base fit potential. And so that now it takes small steps, very small fun. And better. It could take very, very long. Whereas if it's too large, it could just skip over the entire potential and not see it and then go on and search for something else. So it's a fine line between speed for the one and actually not doing. So most aim for a roughly 20 to 50%. For visualization, how it can work, okay? So you have 1 sigma, 2 sigma likelihood distribution. You have your first one, it gets accepted, it's there. Second one, it tries outside, it's not, it tries to accept it, random chance, it fails, tries a new one, okay, it goes. Same for number 3. Number 4, this is lower, and it still gets accepted. That's kind of just how it works. As it then produces through this, you start building up your posterior. Now, this base fit tries to improve itself over countless iterations until you get your match to your data, in this case. Okay, so why now that's the stats for. What about the physics for? Well, it started back, Adam raised them in the late 90s, went and, let's use supernova, the type 1a specifically. And the reason is they have a very consistent way of exploding. Okay, with a very characteristic peak luminosity. And with some calibrations, now especially with set rate variables, you can get quite consistent absolute magnitudes. This makes them standard candles. Not fully standard candles, but close enough that with set rates, they are effectively standard candles. Then you can go and say, okay, absolute magnitude that's calibrated, because they're all very much the same, gives us the distance luminosity. Okay, so you have observable on that side. On the other side, distance luminosity or distance modulus correlates to the distance luminosity. or luminosity distance. So this is now the model side where you connect it. You have your model, in this case, just say flat-hander CDM model, and you can put it in here. It's just your small h. So while you take your square of your h over, that goes in there, and that's concentrated in this come out. So this and this can then be linked to your distance luminosity. So that entire equation is equal to the small m minus big M. That's how you connect the data to the theory. And then, like I said earlier, most people use a symmetric chi-squared Gaussian distribution for its likelihood. You can go more complex, more accurate, but this is easiest case. Now you put this method in, run it with this model, this data, and you get something like this. This is obvious. I mean, people won a Nobel Prize for this back in the day, but it's old. Nothing that you can do. You're just kind of minimizing the space between it based on a likelihood. Okay, but then people said, oh, but we also have CMB data. Let's see what CMB says about our results. And at first, nice, easy. But then as some measurements got better, we got to this problem where we have the 5 sigma tension that everyone is talking about these days. And it had this clear split between your early time measurements, via a CMB being lower, and your late time distance ladder measurements with supernovae, Cepheids, the whole shebang. So then people were like, if you ask the different groups, if you ask CMB who is right, they'll say CMB is correct because they have sub 1% accuracy, while supernova has very large errors. And if you ask supernova people, they'll say it's them because the model is straightforward and CMB's model is better. So the problem became, okay, how do we solve this? And then the sigma 8 tension came and all of these. So people introduced more data sets into the mix, trying to add it. And we already saw it in the next paper. So CB, Planck, coming from Planck data, BLA, more recent with DCs, OSB, CC, all of these, but they all tend to have degeneracies in their parameters. They're the most and a low Hubble constant, and vice versa, high Hubble constant and low sound horizon gives exactly the same model. So how do you distinguish between which of the two is correct? So you have to combine these data sets. Okay, now you can combine them, but then something happened earlier the year. They went and found, what about it maybe the model not being correct? So out of their own thing, unless there is unknown systematic errors associated with one or more data sets, it's clear the Lambda CDM is being challenged by a combination of BOA and others, and that the dynamical. So suddenly, okay, maybe it's not even just the problems in the data set that could lead to stuff like this and sigma 8 tension. Maybe it's the model itself. So everyone is now looking at different models, trying to see, searching for this new concordance model. But how can we do it? Well, if you have a simple, easy model, linear, you can go the old way. Monty Python, it will be able to constrain your model. It's powerful, but not necessarily user-friendly. It's quite difficult to set up. Kobayashi, they wrote Kobayashi specifically to improve user-friendliness, and they have like these nice drop-down menus that you can select what you want to have in your model and stuff. But this also means it's very rigid in its design. what if the model you are trying to constrain does not match what Kobayashi is offering? You can change it, it's possible, but then you have to have that knowledge of how the YALM files work and all of that. So, okay, that becomes difficult if you have a weird model. And then it can be, well, most of the stuff focuses on CMB. They do have other stuff, but it's mostly related to CMB. And we already have this, we need a lot of data sets working combined. Furthermore, everyone in senses are slow and computationally expensive for such a straightforward algorithm. So what about people that does not have access to a server? There was a postdoc at us recently. He has access to a 64-core cluster, just him on his own, and just a Lambda CDM on the CMB data took 4 days. Not everyone has 64 cores just lying around. So it takes a long while. So you can still do your work in these. It's just slow, and sometimes, especially if you're not a coder, it can be difficult to have your work. And above that, even going further, all of these are related to Lambda CDM or similar type of models. Modifying them is increasingly difficult, like seeing with Korea, and going to non-solvable models, non-analytically solvable models that you have to solve numerically becomes almost impossible indeed, because they rely on classing, and classing was never written to allow for non-solvable models. So this is where the simulation comes in. I know this, I can't take it. So Cosmo, for in Afrikaans, Cosmology, that's why it's a game of the sea. And simulator, or in sense simulation. And it's utilizing Zeus and MCMC, the two MCMC engines, to run a vectorized map chain. By this, we mean when I tell you, here's a model, y equals 2mx plus 5. You can visualize that model without needing to calculate the y value at each x. You can, it would have the shape. Now, for computers, if you have arrays, it's basically you need to calculate the y at each x. But if your model is vectorized, then the computer can also understand the function as a whole and does not have to run loops and arrays, which saves time. They work good, but they do add up. Even if it's few split seconds per iteration, if you're doing 100,000 iterations, it adds up. So the idea came to completely vectorize this thing to see if we can really save time. And then specifically for modified gravity or alternative cosmologies. It's also written to be modular, so you can just add on without needing to worry about breaking the code. Okay, so it's a quick example. This was a paper from Shamble. It was due to these models that I write the code, and it's non-solvable unless n is zero. Okay. So these priors, and for this demonstration using Pantheon plus shoes, nicely calibrated to separate variables and the big data set. BCDR2, since it's the one that gave everyone a lot of work to do, and BBN to help calibrate with the RTE, the sound horizon Hubble constant, degeneracy, and then just for interesting CC and JAS, it's the original paper of minutes work on. Now, what do you have to change? First, your model. You have to introduce it into the code. This is like, you must think of Cosmology as like a library with each book is a different model, and you take your model and go put it in the library. Now, it looks complicated, but if you look at the details, it's only your free parameters. Well, I don't know what free parameters you want, And then F, which is basically just your frequent equation minus, so the left-hand side minus the right-hand side equals to 0, which you're trying to minimize for F, and the first order derivative. That's it. The rest in here is just safeguards, and you can ask even ChatGPT which safeguards add for this model. It's there just that since it's a non-linear model and you're introducing numerical simulation inside the numerical simulation, there might be edge cases, but yeah, it's a basic Newton-Raphson method. Okay, so you put that in. Now you put in the library, you go to the library person and like, okay, this book has this name, whatever you call it. You can make it up. The function name, which you set up there, that it knows which book to go get. So if you say the F1 CDM, it knows this is the book it must go get, and then the free parameters again. If there's restrictions on this model, particularly there's no extra restrictions, like let's say your model has a 1 over omega minus delta. Well, omega and delta cannot be equal to each other, but the MCMC doesn't know that. So it might test random combinations and they might link up. So if you add that, you can add that also in, like there's your restriction, and then again, just that same model key, and it's it. And that's it. That's how you add your new model into Cosmology. Nothing else. From this, you can run your MCMC. So then you call your model, that's the one I want to run. The model key, put your data sets that you want. I want likelihood between all of them, and then this one, and I want the statistics to be compared to the lambda CDM. Pick your normal stuff, and the code runs. That's straightforward. So you can call it with different things. I'm not going to go into it too much, but we have a reason function. If you're running a big simulation that's been running for like CMB that runs a couple of days and it crashes, you can just say go on, and it goes on. Override it, will sort out your stuff and rewrite them. Or if you're working on different projects, you can just put your project name there and it will make a directory for that project to keep all of them safe together. So it's just fun extra arguments to make it more personalized to your. Now, I'm running it here just to show I'm doing a local multiprocessing. And it's for the I-COOP project. That is just how many times consecutively over a period of 100 iterations must the values not in for it to be considered correlate. So it will search and search, but if it starts to recognize the values aren't changing anymore, it's all of them, they are staying right there, they are never getting accepted to move out, then it's like, over the last 100 iterations, it didn't move. So I think it's correlated, it's at the answer. This tau consecutive just increases that. No, not just 100, make it 500 iterations before you are convinced. It's just the goal, you having more control over the statistic, and then you can add latex in, make your process nice. It then starts up with a basic thing, shows you what you chose, how it's reading in. You'll see here it added extra parameters, free parameters. So it recognizes that in your model, you're not using these free parameters, but they are necessary for the observations you are running. For instance, if you look back at the, which one is it? Yeah, so this would be your model, which only in this case has omega m. But to complete the entire model, you still need H naught as well. So it would like your model doesn't have this. I'm just adding it in because it's necessary for the run to complete. Okay, after that, it then runs and you get an initial condition based on some. And look at it, it's a couple of minutes. on a quite big data set. And then for a more complex, so that's for lambda CDM. Here's for the F1 model, the non-linear, and it took a tiny bit longer. This model earlier the year on a standard way of doing it, not vectorized, took me and Shamble 60 hours to run. So getting it down to 4 minutes was quite surprising. Just by limiting, we are still surprised of that. And then it will print out your base fit values in later, so you can just get a folder and give you the statistics, the AIBMs. AIC. Now, before I go on, I want to quickly show you here. So this is how it generally looks. When you run it, it automatically makes the change, which it can then reuse.
Can you share your whole screen because it's not being recorded?
Okay.
And also turn up the volume. You control now if anybody speaks.
Okay. So yeah, it creates the so this is Cosmology. When you come in, it creates change in your project file that it says, so it will label them which model you were rating it for, what observations. It also then creates these plots for you. Firstly, let's go into the F1. We'll first show you these, and this is how it got calibrated. So you can see here, started rough, and then it started finding what it was looking for, and it turned, and then here it crossed the threshold line of less than 0.01 movement across 100 iterations for all the parameters.
So we show that it is converting.
Our value just means that you need more than one or how many sequentially to match it. Then you know really you got it. And this live updates as the thing runs, so you can see what's going on inside. They have an idea, and it does it for all of them. Then it calculates your corner plots for you. So there it is. Let me bigger. So it creates your corner plot, and then above you'll see since I enable, it then adds a table onto your plot. It's easy in this case if you want to work with other people. Look what this one gave. Values are with your plot. For publication, then you can just put it off to keep the separate and then in a nice table. Have that. And then lastly, create your base fits for your the combination. So this was now a combination of Pantheon. So it shows you how well your model does on Pantheon. That same model on DCBR2. And since BBN were used to calibrate it, it also then gives you a RD value from the BBN that were used to get this constraint, basically. And then same for here, just for to say, if the two were compatible, like if I were to use JLA and Pantheon Plus, it would recognize both are supernovae, and then it would combine them into one. So then you can see how it fits both of them at the same time. And this automatically gets created for you. Then lastly, also creates these statistic tables to keep your results for later, where it gives you the align tables for each parameter to have for later, and the stats, what it has, and then a little bit of interpretation, but real physicists don't really need it. Or things that you should at least look for towards the results that you got. So in this case, it's like if there's weak evidence against this model, or report. So just to help you, but it's not the final say. Yeah, and so we are going forward now with this, and it totally took 10 minutes. And since it was vectorized, it only ran on one core. When it's vectorized, it doesn't do multi-core. So as you can see on my PC, I literally just used one core for 4 different fits on 2 different models, including a non-linear, and it took me 9 minutes in total. Of course, doing something like CMB will still take quite a bit. It's not very fast.
So this was fast because you were just looking at supernovae.
In this case, supernovae, BOA, CC, and BGN. So we had quite a bit.
Yeah, okay,
But yeah, they are much more straightforward to constrain than CMB. The problem with CMB is you require a Boltzmann solver. So you have your model, you send it to Classy, it creates a spectra for you. It takes that spectra, sends it to something like Click. Click does a full Boltzmann solver on it, calculates everything, and then returns a likely value. So where for all the others, you have one equation, it calculates it done. It has to send this thing around, so it builds up time. So we are trying to do it faster, but at this stage, the best we can do is match Cobaya. But yeah, for non-linear, I guess it's not that bad. And Cobaya is the fastest one between them also. So yeah, at this stage, it's not yet publicly available. The code can be found on my GitHub. There.
Yeah.
But yeah, that's still a bit outdated. It was before we did all of the vectorization. But first we want to complete fallbacks like for these degeneracies that we can tell the person you want to run CMP, but you don't have a Boltzmann solver installed. Please first install it and then go on with the rest or stuff like that. But all of these take extra coding, and then we want to complete the CMB physics. At this stage, it runs, and the values look fine, but every single day there pops a new bug. It's how it goes. So then this one might interest some of you. So Eleonora Delavertino, she and a PhD student from Poch, they are working on these interacting dark energy models, and they want a plug and play type thing with already all of these interacting dark energy models loaded up with their setup and then all of their boundary conditions if you want to go into phantom regimes, negative energy regimes, whatever, all of that, and then you can just run them and study what it does. We are getting to that, but I've thought out all the other bugs before introducing a big thing like that, but it's coming, it's in the pipeline. We also want to add these dynamical equational state plots, since Daisy kind of everyone now wants to add it in their work to do it automatically. Look at other data sets, try to increase our library. We don't have the same library as something like Goya, but we are adding new ones in every single day. So that's very different.
Thank you so much. Very impressive. Yeah, I'm very impressed by this. By this code.
Yeah.
So, questions and comments? When do you estimate that it will be complete? In a public, the press public.
So we want to make the original plan was before I come here. Now we are looking, hopefully within the next month, we can make it publicly available. We are being held back by the CMP stuff. Like, it works, but it breaks a lot of the vectorization due to sending these things around. So we are losing time. And since the code is done to be vectorized on one core, it always wants to go to multiple cores in a non-vectorized way, which makes it difficult for others. If you just run CMB, sure, then running on multiprocessing would be fine. But if you want to compare it with the others, yeah, then it would force all of them onto the multiprocessing side, which is technically slower, even though you're running full cores. So we are struggling with that bug. Robert Profabere's student, he found a love for it and he's working on it. He's actually even considering making a new Boltzmann solver because Click, I don't know if you guys have worked with Click before, it's very difficult to install. That's kind of half of the reason I wrote my code at the beginning on my own, because I could never get Click installed. That documentation does not work. And then even Korea realized the issue with Click installation. So they built in a version of Click into their own installation that if you get them installed, Click should work. But yeah, so Korea is a good one in that way, but Click makes it difficult even for us. But the last I heard, Robert said he got down to at least the same time as Korea. So hopefully it's going soon. And then the IDE stuff, that will start building in as soon as we can publicly release this one. So I don't think it would take too much time since most of the things are already included. We can already add new models, we can already add restrictions. The only thing that would be different for them is having these switches where, okay, for this type, if the person wants to do phantom regimes, then only these restrictions are valid. So it will be like switches, but that should not be too hard.
Okay. So let me understand something. If you, for the supernovae, the simplicity of the interaction with this code is because you just can define the background model. Like the function, you put the Hubble function for
yes, it basically becomes fit a model to a data.
Yeah, but how do you? Yeah, but the Hubble function is good for the background evolution.
Yeah.
But now and this is compatible with the supernovae, the VAO,
yeah,
and the other things except CMB.
Yes.
For the CMB, you need to put the perturbation equations of the model.
Yes. Well,
this is where the Boltzmann solver is.
Yeah. So at this stage, I'm not exactly sure how Robert's doing it, but he has to set up an extra classy file that would take the model then 4 classes. So it's an extra step. And yeah, then classy sets up how everything should run and sends that to it, Click to solve. So basically Cosmolator is just like a wrapper sending the stuff around for CMB and doesn't actually calculate it itself.
So but if I forget about CMB and I just want to explore the other data sets, I just put my background, the Hubble function.
Yeah.
And it produces all the plots and the statistical analysis.
Yes. Yeah. Then if you're not looking at CMB, then it's basically how I did it here. So you then just
and we don't have to pay for that.
No, it's Python. Python is free. That's why I asked the other person. So then you just put your model, put it in a library, and then you can code it.
Yeah, so at some point, when it is working, we will organize something else at school, probably, and teach us to use it.
Yeah, Prof. Baby has been pushing me for this, and I've been pushing ChatGPT because sometimes the errors are so weird, and it's like, then I give the ChatGPT, and it's like, he gives the thing, and I'm like, nah, but this can't be this, and some of them were weird, but Yeah, the aim what I originally thought about this was basically Shamble kept bothering me to run his model or check his model. And he was using my old code, but my old code, which I wrote for my master's, I was not a very good coder back then. It was my first real big coding project. And it worked, but inefficient, and you had to know the detail of the code to know what to change and stuff. And Shamble brought it to him, he figured it out and stuff, but whenever a bug came up, it came to me. And I was just like, I want to write a code that people can just, they must do as few as possible things to take their model and put it in. Nothing else, the code should do everything in the backside. Exactly. So that was the aim for it. But we can't get at this stage for all except CMB. I'm confident we are beating the other ones. CMB, I think Korea is still technically faster. But yeah, Korea has the problem of you can really not change your model that much. And if you do, you need to know a lot of coding expertise, where mine you don't. So.
Okay, so thank you so much for presenting this thoughts of us.
They're the first people to get a full talk. Like Prof. Bebe, and they know about it. Some of the other students already use it, but yeah, first actually. Yeah, but
So this is wonderful to finish our So thank you so much for the contributions, for your passion, for your enthusiasm.